Okay, so we have 5.4b, and 5.4b is going to be a kind of a putting it all together for us. So in your 5.3 assignment, hopefully you kind of heard the term a lot, one-to-one property for exponential equations, okay? And the conclusion that you should have made for one-to-one is that you want your basis of your exponentials to be the same so that all you have to do to solve is set your powers equal to each other. Okay. And then from there, you're just using your algebra skills to get the variable by itself. Okay. Next, also there was the one-to-one property for logarithmic equations. So your one-to-one property for log equations is that you want the logs to be the same so that you're setting your arguments equal to each other. Okay. The next thing that we're going to talk about is from yesterday's, from 5.4a, was our inverse properties for exponentials and for logarithmic equations. If I have this is supposed to be a little a, I don't know why it became a big A, but if I have log base a of x and I want to get rid of the log, I'm going to raise it to an exponential of the same base of the log. Okay. And what that does is going to eliminate the log, and all I'm left with is my argument. Okay. If I have an exponential raised to an x or a variable, and I want to get rid of the exponential, I'm going to take the log of the same base, and they'll cancel each other out. So that's how the inverse properties work for that. Okay. So, when we were describing some strategies for using the one-to-one properties, what is it good for? It is good for rewriting the original equation in forms so that allows the use of one-to-one, okay? Exponential or log functions. We can rewrite an exponential equation in log form and apply the inverse property. We also can rewrite a log equation in exponential form and apply the inverse property, okay? So that is what is going to be useful for. All right, we're going to do an example first. Our first example that we're going to do, we're going to do two parts. So if you could split your example one part, we're going to do example A. So for example A, we're going to do log base 8 x equals 1 to the third, okay? And we want to solve for x. So using our properties above, we can use our inverse property. I can raise this log to an exponential base that's the same base as my log. So I'm going to 8. And when I do one side, I have to do to the other. Okay. What's going to happen here is that this is going to cancel out, becomes 1. And I'm left with x equals 8 to the 1/3. Okay, back in Algebra 2, we learned that if I have a number raised to a rational power, that means I'm taking the root of that. So x equals the cube root of 8. And the cube root of 8 is 2. So my x equals 2. Okay, so that's an example using the inverse property. So what do we use here? We use the inverse properties. Okay, now on this side, we're going to do example B. With example B, we're going to talk about trying to get one-to-one when it seems impossible. So if I have 5 raised to the x equals 400, it may seem impossible for me to get 5. However, we're going to work our way through it. So 400s can be written as 4 over 100. 4 over 100 reduces to 1 over 25. Okay. 1 over 25 can be rewritten as a exponent with a negative power. So that's 25 to the negative 1. So now I'm down to 5x equals 25 to the negative 1. Well, luckily we already know that 25 is 5 squared. So now we have 5 to the x equals 5 squared times negative 1. Why? Because their negative 1 is already there and it does not disappear. Okay. Now that it's 1-to-1, to solve this, all I'm doing, I'm ignoring the exponent, the bases of the exponents, and I'm taking the powers and setting them equal to each other. So now I have x equals 2 times negative 1. So therefore, x equals negative 2. Okay. All right, so continuing. Now we're going to talk about how we can solve exponential equations, okay? Exponential equations, meaning that we have typically b to the x equals, let's just say, a constant, a number or something, right? B to the x equals something. How can we solve that? So we're going to write out some steps for us to solve. So the first thing, well, before we get started, you want to make sure that your exponential is alone. Okay, you want to make sure your exponential is alone. And then once it is, we're going to follow these 3 steps. So step 1 is we're going to take the log of the base, of the exponential base. So we're going to take the log with the same exponential base. After we take the log, we're then going to apply all of our inverse properties. So not just our exponential and log inverse properties. We're going to also apply inverse of addition, inverse of multiplication, and such, okay? And our third step is going to be to simplify. All right, so let's do a quick little example. All right, so following these 3 steps, if I gave you 10 to the x equals 90, okay? So my exponential is by itself, so that's good to go. Next, I'm going to take the log of the base. Well, my base is 10. Because my base is 10, that means I'm taking common log. So I'm going to have log of 10 to the x equals log 90. Okay, using inverse properties. Remember, this is common log, so even though I don't see it, the base is 10. Using my inverse properties, these are going to cancel each other out. My exponent is free. So we have x equals log of 90. And that is my exact value. If it asks for an approximate, then I would put log of 90 in the calculator and I get an approximate value, okay? So it's completely simplified. I can't go any further, and that's it. All right, so let's give an example for you to try. No, we're gonna do a natural log example, sorry. So we're gonna do a natural log example together. I'm sorry, I thought I put enough space, but I did not. So it's gonna kind of flow down to the side if you're following along using your notes. So the problem that we're gonna do, we have e to the x minus 2 minus 7 equals 59. Okay, so again, we want to make sure that our exponential is by itself. So when we look here, our exponential has something outside of its bubble, that minus 7. So in order to start following my steps, I have to get rid of that minus 7. So I'm going to add 7 to both sides. So I'm adding 7, adding 7. So now we're working with e to the x minus 2 equals 66. Okay, with a natural log, with e, in order to cancel it out, we can't just use common log. We have to actually use natural log. So we're going to take the natural log of both sides. I'm going to squeeze it in there. So natural log. This is an inverse rule. I have natural log of e. This is going to equal 1. So we're left with x minus 2. It equals the natural log of 66. Now I just need to get my x by itself. To get my x by itself, I'm going to add 2 to both sides. So I'm left with x equals the natural log of 66 plus 2. Okay. All right. So at the top of your paper, you should have some room. I would like for you to do just like you do, for you to try really quick. If you had 11 to the x equals, let's say 5. Quickly take a moment and find what x equals. Okay, so notice here that our base is not 10, nor is it e. So our base is 11. So when you solve this, you should have taken the log base 11 of both sides. So we would have log base 11 of 11x equals log base 11 of 5. Okay, what happens here is that using inverse properties, this is going to cancel out. So then therefore your answer should be x equals log base 11 of 5. All right. Okay, cool. Let's continue. So next it says, what do you do if you're solving logarithmic equations? Okay. Key step again is you want to make sure that the log is alone. So you want to make sure there's nothing being added, subtracted, multiplied, or divided outside of the log itself. Okay. So you want to make sure your log is alone. All right. Then you're going to follow the steps. This time we're going to, I'm going to say, I think I'm saying this correct, raise to the exponent of the same base. Okay, so we're going to raise it to the exponent of the same base. Then we're going to use our inverse properties. And then we're going to simplify. Okay. All right, so let's do a example together. And I think for that, I'm going to, before we actually do our example, but on the side, I'm going to use a natural log, for example. So we have 4 natural log of 5x equals 8, okay? And I'm solving for x. First thing, my log has to be alone. So my log is not alone. In order to get my log alone, I'm going to have to divide by 4. So I'm going to divide by 4. And now it's natural log 5x equals 2, okay? Now, to get rid of the natural log, I'm going to raise it to the e. And what I do to the 1 is on one side, I'm going to do to the other. So it's e to the natural log of 5x. E equals e squared. Well, inverse property tells me that e raised to the natural log cancels out. So I'm left with 5x equals e squared. X is not quite by itself, so the last thing I have to do is divide by 5. So when it's all said and done, I'm left with x equals e squared divided by 5. Okay? All right. Let's do a log. So our actual example that we're going to do is log base 6. So log base 6, 4x minus 7 equals, not equals, I'm sorry, minus log base 6, 8 minus x. Okay, so the first thing we want to make sure is that our logs are both by themselves. It is supposed to be equal, y'all. I'm going crazy. And then second, now we're going to raise the exponent of the same base. Raise it to the exponent of the same base. Well, our bases are 6. So we're going to raise both sides to 6. Okay? What this allows us to do is now to apply our inverse property. Inverse property says that those are going to cancel out. And all I'm left with is 4x minus 7 equals 8 minus x. Now I'm going to continue using my inverse properties to get my x's by themselves. So I'm going to combine like terms, which means I'm adding x to one side. And I'm adding 7 to the other. So canceling that out. And we're going to be left with 5x equals 15. My last inverse property that I need to do is divide by 5. So I'm going to divide by 5 and divide both sides by 5. That's going to cancel this side out. And then I simplify. 15 divided by 5 is 3. So x has to equal 3 in order for this to be a true statement. Okay? Ta-da! You did it. All right. Our last part of our notes is a word problem example, a real world example. Okay? So applying the skills that we just did to solve a real world problem. Here it says use the formula for continuous compounding, which is A equals P times e to the RT, and find out how long it will take $1,500 to triple in value if it is invested at 3% interest compounded continuously. Okay. So the beauty here is you're given a formula. You have to identify the value of the variables from your formula and go from there. Okay. The 1,500, that's called our principal. That's our initial amount. Remember, the P is usually what's in front, and your P, your A is usually your initial value. So we're at 1,500. Okay. We want it to triple in value. So we want our amount over time to become our A. So over time, we want our A to equal 4,500. Okay. Next, it tells us our rate, our percentage. So our R equals 12%, which equals 0.12. So I now have all the values and I'm going to substitute them in. So we have 4,500 equals 1,500 times E to the 0.12 T. And now our goal is to get to T, to figure out how long it's going to take me to reach that amount at the rate I'm saving. So here is my exponential, and our exponential needs to be completely by itself. So if my exponential needs to be completely by itself, that means I need to divide 1,500. And 4,500 divided by 1,500 equals 3. So we have 3 equals E to the 1,200ths times T. Now that my exponential is by itself, I can take the log of it. So I'm going to take the log. The log for E is natural log. So I'm going to take the natural log of E. What I do to one side, I'm going to do to the other. It's going to cancel out. So I'm left with the natural log of 3 equals 1,200ths times T. The last thing I need to do is divide by 1,200ths. Okay. So I'm left with T equals natural log of 3 divided by 1,200ths. Am I going to tell an investor, oh, it's going to take you natural log of 3 divided by 1,200 years to make this happen? No, I'm not. I'm going to figure out the approximate value of T. So to find this, I'm going to plug this in the calculator, which I've already done, I believe. So when I plug natural log of 3 divided by 1,200ths, I get approximately 9. We're going to say 9 2/10 of a year. So approximately 9 2/10 of a year in order for this to happen. Okay. All right. That concludes 5.4B.